All right, I'll start the session now. Am I audible? Hello? Am I audible to everyone?
Yes, ma'am.
Okay. Hi, I'm Shreya, the TA for this course on Introduction to Probability and Statistics. So, for the next couple of weeks, I'll be discussing briefly the content of the weeks, and then I'll proceed to discuss a few of the problems which will help you, which is intended to help you solve your assignments. Now, please feel free to share your feedback and make this opportunity, use it to your advantage, and try to, the thing is, try to follow the lectures before coming and attending this session, so that will make things easier. And if you have some doubts regarding the course content, then you can come here and ask me. So that's one thing. And before moving on and carrying on with this doubt clearance session, uh, I would like to know all of you who all have joined, and what is your background, and I mean, what is the intent of taking this course. That will be helpful for me to design and make further. That will help me prepare these slides for the upcoming classes. So please go on and introduce yourself. Since this is the first class, I would like to know all of you, and then I'll just jump onto the content. Yeah, we'll go alphabetically. Afif. Okay, anybody. Just give me what your background is and why you have taken this course. That's it. Please don't feel shy. There's nothing to feel shy about. This is just to know what sort of expectations you have from this course. Afif Manzoor, are you there?
Okay, so since nobody is talking, I'll start.
Yeah.
So my name is Vedika,
Hmm.
and I actually graduated with a bachelor's in pharmacy back in 2021, and I've
Okay.
been working as a data analyst now.
Okay.
So I thought to make, since I come from a non-technical background, I wanted to learn more in depth about the technical aspects.
Okay.
So I am taking this course, and also I do need the credits because I am planning for masters.
All right.
So I want the credits too. So
Okay. Thank you, Vedika. Anybody else? Any UG student over here, or are all of you working?
Good afternoon. I'm Harshini JS, and
Hi.
I'm doing my UG in maths currently.
Okay.
I just took this course just to develop a basic knowledge about statistics and probability.
Okay. You are doing MSc,
Yeah, no, BSc.
BSc in maths. Okay.
Yeah.
Okay. Anybody else?
Ma'am, I am Vikas Saroha,
Hmm.
and
Hi,
I'm
Vikas.
working as scientific officer in Bhabha Atomic Research Center.
Okay.
And I'm doing PhD from Homi Bhabha National Institute.
Okay.
And my doctoral committee recommended this course for me,
Okay.
so that's why I'm attending it.
Okay. Your background is?
I'm a mechanical engineer, ma'am.
Okay. Fine. Anybody else?
My name is Sideep, and currently I'm doing my first year of BSc in Bangalore University with BSc Statistics.
Okay.
And I've taken this course just to enhance my skills and get a depth knowledge about statistics and probability.
All right. So all of you have had, I believe you all have had maths in your plus two level. Yeah. Okay. Anybody else? who wants to share their background?
Hello, I am Avinash Ranjan from I am MTech second year student. I am taking this course to change my. I am basically electrical from electrical engineering, but
Okay.
I am taking this course to enhance my internship opportunities in this field.
All right. Thank you.
And also, I have one exam to give, which has syllabus overlapping with the statistics.
Okay.
That's why I took this course.
All right. Okay. Anybody else? Anybody else who wants to share what their background is and what is their expectation? Okay, if not anybody else, then I'll start the session. So today's session will be very basic, and the problems I'll discuss that will also be very basic. But in the course content also, and here also, I'll be recapitulating a few concepts on which the topic or the subject is primarily based on. So I would like you to understand this very properly and clearly so that you're able to understand your assignment questions that will help you in fulfilling your credit requirements. And also these are very preliminary and introductory concepts which will, and upon which the further future concepts will come, and you have to build upon these concepts. So if you have any doubt, anything you want to clarify, please don't hesitate to ask me. Okay, and I'll try my best to answer it in class. If not, then probably in subsequent sessions I'm going to answer. Okay, so shall I start? Okay, thank you. I hope you can see my screen, right? Okay. All right. So the first thing that was discussed during the class was the meaning of a random experiment. So we say that an experiment is random if its result cannot be determined beforehand. So like an example, we can talk of tossing of a coin, rolling of a die, or number of accidents in a day, number of printing mistakes in a page. Until and unless you perform the experiment, and even while you're performing the experiment, the outcome that you receive, it is not predetermined. Like for example, if you toss a coin, it could be a head, it could be a tail. If you roll a die, it could be anything between 1 to 6. And on any typical day, we don't know what the number of accidents will be. It's not predetermined. So experiments of that sort are called random experiments. Now, the outcomes of a random experiment could be finite, could be countably infinite, could be continuous, uncountably infinite as well. For example, if we talk about this specific thing, tossing of a coin, this one, the outcomes would be head and tail. So the outcomes are finite and it's countable, 1 and 2. For this one also, it's finite. This one, it could be countably infinite. And temperature of a city, if we say that, let's say the temperature could be anywhere between 25 to 50. So x such that 25 less than x less than equal to 50, this is countably infinite. I mean, there could be so many x's taking values between 25 and 50. Okay, so whatever I am listing out here, as an outcome. So 0, 1, 2, these are all outcomes of a random experiment. Now, so the set of all possible results or outcome of a random experiment is denoted by this symbol, which is called as omega, and this represents the sample space of an event. So for tossing of one die, the sample space is H and T. So suppose if I have two coins tossed, can anybody tell me what the sample space will be?
Head and tail.
Okay, so head and tail. So I'm tossing two coins.
There will be 4 outcomes: head, tail, 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 head, head, and
Yes, head, tail, tail, head, head, and tail, tail. Okay, if I roll 2 die, then how many outcomes can we get?
36 in total.
36. Yeah, correct. If I count number of accidents in 2 consecutive days, then how many outcomes can we get? We don't know, right? Because this is a infinite set. So it could be anywhere between 0 to infinity, but it would be a countable one. Do you agree with me? Okay.
Yes, ma'am.
All right. And also one thing that should be noted, that this sample space could consist of numeral elements and it could be non-numeric as well. Okay. So then we learned about an important kind of an abstract topic, which is known as sigma field. So sigma field is defined over your sample space omega. Now, what does it mean to be a sigma field? So a collection script F of subsets of omega which satisfy these 3 conditions they will be called a sigma field. So what are the 3 conditions? The first thing is the sample space should belong to script F. This symbol means belongs to. Hopefully all of you know, but still if there's someone who doesn't know the meaning of these symbols, I'm just going to mention it here. Okay, so omega should belong to that collection of subsets of omega. Okay, this is one criteria. The second criteria is if let A be an event let A be a subset of these, let that set belong to these collection of subsets. Okay, that is script F. Then A complement should also belong to F. Alright. If A belongs to F, script F, then A complement should also belong to script F. That is criteria number 2. Criteria number 3 is that, let's say we have A1, A2, A3. These are events which belong to script F. So if we have such a sequence of events, then their countable union, that is union of I equal to 1 to infinity, should also belong to this script F. So what are these AI? AIs are elements of this collection. Alright. So the most trivial sigma field is made up of 2 sets. That is phi, that is the null set, and this is the sample set. Okay, so omega, let us verify the conditions. Omega belongs to script f, omega is belonging here, omega belongs here, then omega complement, that is phi, it also belongs to sigma field, and no other, so let's say these two only are defined, phi and omega. So phi union omega will be omega, which also belongs to script f. So this is the smallest sigma field that can be defined on any omega. Is it okay? Now the next thing is the largest sigma field. So the largest sigma field is called the power set, which will contain all subsets of omega. Okay, and also we discussed a special case when omega is this symbol stands for real line or real numbers. Okay, so if when omega is the real line, then the largest sigma field will be the Borel sigma field, which is generated by sets of these kinds.
Excuse me, ma'am.
Hmm.
Ma'am, in this set, Borel sigma field, there is not a complement of interval A, comma B is not there.
No, this is not the Borel set. The sigma field which will be formed by sets of these kinds, they will have to be present here. For example, if I say this is one element, let's say, then the complement of it will be minus infinity to A union A to infinity. Okay. So this one should also be present in the Borel set. So typically a Borel set should comprise of sets of the form minus infinity to A. A belongs to real line. So the sigma field which will be formed with all these sorts of elements and sets, that will be the Borel sigma field. If I restrict myself to this one, then that is not my Borel set or Borel sigma field, because this union element should also be present over here. Is it clear? So the sigma field that will form with sets of this type, that will be my Borel sigma field. Is this clear? All right. So next, what was discussed was the definition, axiomatic definition of probability. So for any definition of probability, we need a probability space. So if sigma is the sample space and script f is the sigma field defined over sigma, then a real valued set function p which satisfies these three criteria, that is called a probability. Now probability of A should be greater than equal to 0 for all. This is the symbol for all. For all A belongs to script f. Probability of omega should be 1. And if A1, A2, A3 and so on are mutually disjoint events in scriptf, then their union should be summation of the individual probabilities. That is the sigma additivity rule. So this sigma additivity should hold. So if these three conditions are satisfied, then we call this P to be a probability. So let's say I have a container like this. This is my scriptf. And this is my real line, let's say, minus infinity to plus infinity. Here somewhere I have 0 and here somewhere I have 1. And here we have A1, A2, all sorts of events. Omega is also here, okay, because this is a sigma field. So what this probability function is doing, it is mapping some subsets from this scriptf to the real line. So this P is the mapping function. Whose domain is this one. So if P is the mapping, then this scriptf is the domain and 0 to 1 is the range of this function. This P is actually a set function.
Ma'am, is that mapping function a random variable definition sort of thing? Because even that we plotted on a real line from the omega set, right?
So the random variables will be these events if you have to, make a concordance, because we make out a probability of any random event and that will be something between 0 to 1, right? So these events which I am considering in scriptf, those later on we'll go and see will give us the definition of a random variable, because A1, A2, A3 are outcomes of some random experiment, so they are random outcomes. So you are right in that way, but to start from the basics, let these be some events which belong to the scriptf, and probability will provide some sort of a mapping from these sets to this 0-1 range.
Okay, got it.
Okay. All right. So as part of examples, we saw these three. So this is an example of when you would roll a die. Sorry, this is for tossing a coin. Extremely sorry. Okay. So our sample space is either head or tails. I'll say tossing a coin once. This is my experiment. So scriptf would be omega has to be present. Okay, so omega is here. Then if h is present, h complement, that is t, is also present. Likewise, if t is present, t complement h is also present. Omega is present, so phi should also be present. And if we take unions, then that is also present over here. Alright, so this is a valid sigma field. Now we are defining the probability on sigma field. Okay, so probability of, yes, please call me Shreya.
Is there any rule of assigning probability to getting head 1 by 5?
You're not audible. Can you be a little more loud?
Ma'am, is there any reason of assigning probability to getting head as 1 by 5?
No, we could assign it to be anything. Just we have, in order to make it a probability measure, we have to follow these 3 rules that were discussed. It could be 1 by 5, it could be 2 by 3, it could be point something something, anything. As long as it is greater than 0 and probability omega equal to 1 and these sigma additivity criteria is satisfied, we are good to go. So instead of this 1 by 5, 4 by 5, I could also give 2 by 3, 1 by 3. And usually from what we have done, and we'll also learn it as the classical law, what we take is half and half, that is equiprobable in case of an unbiased coin. Okay, so we are free to define this. Once it satisfies all those 3 criteria, then only we can call it a probability. So if I have to see, so probability of omega, that is 1. This is satisfied over here. All probabilities are greater than equal to 0. Any A, nothing is negative. So the first criteria and second criteria is fulfilled. The third criteria was what? That probability of A1, A2, if we have to, and then union of AI, probability of union of AI should be summation probability of AI. So if I have to take a union of all these, then this should be mutually disjoint. This is also something we should take note. So here disjoint events are this one, and this one. So phi union H union T would be probability of phi plus probability of H plus probability of T. Phi union H union T will be probability of H and union T. So it will be 1/5 plus 4/5. Since these are disjoint, minus 0. So this is 1. And if we add individually 0 plus 1 by 5 plus 4 by 5, this will also come out to be 1. Is it clear? Any doubt? So we have to keep 3 points in mind. Probability of A for any A should be greater than equal to 0. Probability of omega should be 1. And A1, A2 disjoint. This thing we have to bear in mind. If we have disjoint events, then probability of union AI equal to summation of probability of AI. This will only hold if sets are disjoint. Disjoint means A intersection B equal to phi for all A and B. Not for all. Like when this holds, then we'll call 2 sets to be disjoint. No overlap, no intersection. Is it okay? Alright. Then we proceeded to this example where this was the sample space was here, the sample space is countably infinite. Here the sample space was finite and countable. Okay, here we have countably infinite. This is the sample space, and let the script f or sigma field be the largest sigma field on omega. Also, one thing we have noted, that script f is not unique. You could define multiple script f's. The smallest one is phi and omega, and the largest one is the power set. So let script f be power set in this case, and if we assign probabilities to each and every, so these elements, these are all omegas. Okay, so probability of omega is 1 by 2 to the power omega plus 1. So if I say probability of 0, it is 1 by 0 plus 1 is 2. Probability of 1 is 1 by 2 square 4, so on and so forth. So all the probabilities defined on each element, they are greater than equal to 0. So condition 1 is satisfied. Condition 1 is satisfied. Now second condition, probability of omega. So omega will be union of this one, this one, this one, this one, and the entire set. So this thing we can, if we sum it up, like these are all disjoint elements, nothing is common with one another, so we can just sum it up. That's what we are doing. Summation omega equal to 0 to infinity probability of each of the individual elements, which will be equal to summation omega equal to 0 to infinity 1 by 2 to the power omega plus 1. So if we just put it here, we'll have half plus 1/4 plus 1/8 plus dot dot dot. Okay, so if we take half common, 1 plus half plus 1 by 2 square plus so on. Half into, this is an infinite AP series. What is the formula? Anybody remembers?
A r के power n r के power n minus 1 divided.
So this one is half. So what will be this one? This is the first A, and r is half. So A by 1 minus r. So this will also be half into 2. That is 1. Okay. Alright. So we'll move on to the next one. So this is the sample space, which is uncountably infinite, and script f is the Borel sigma field on R intersection of this intersected with this sample space. So then if we define this thing, probability A, such that this is defined as integration over a certain range A, e to the power minus x dx. So essentially what it will mean is that it will be area under this curve falling within this range that is defined by the set A. Okay. So here, since this is area, it will, whatever be A, probability of A will always be greater than equal to 0. Probability of omega will be integration 0 to infinity to the power minus x dx. So that will be e to the power minus x minus 0 to infinity. So this thing will be 0. If we place minus infinity here, e to the power minus infinity is 0, minus of minus e to the power 0 will be 1. So this will be 1. Alright, and if we take disjoint subsets, let's say probability of a union of AI, where AIs are disjoint, then the area, let's say if we split it up here to here, here to here, those kind of things. So union will be the same, the area will remain same if we take union, and if we just add up these small chunks and then sum it all up, then we are going to get probability of union of AI, where AIs are disjoint. So criteria 3 is also satisfied. Is it okay? So with these preliminary concepts, we also discussed few properties of probability. So the first one is probability of phi is 0. The second is this one. If we have two events defined on the sigma field and they are disjoint, then probability of A union B will be probability of A plus probability of B. The third one is probability of A complement will be 1 minus probability of A. Now we have to note the difference between this one and this one. This holds true when A and B are disjoint. But when they are not disjoint, so if we have something like this A and something like this B, then this is going to hold. But if we have overlaps, this part is A intersection B. So then probability of A union B will be probability of A plus probability of B minus probability of A intersection B. So if we have to make some sort of a similarity, if we want to get what is in A union B means A total, B total. So if we take A, then A intersection B is included once. If we take B, then also A intersection B is included once. So this part we are counting twice. So in order to avoid that, we'll just take out one probability of A intersection B. Okay, this is just to, just to remember.
Ma'am, I have a doubt. A and B are events, right?
Yes.
Under F. So since they are mutually disjoint, can I also say that they are independent events?
No, no. Thank you for this question. disjoint doesn't mean independent. Sorry. So if we have probability of A intersection B equal to 5, then we call it as disjoint. There is no overlap. But if this holds probability of A into probability of B, then we call it independent.
Okay, got it.
Okay, disjoint doesn't mean independent, though it might seem so. This is not true. All right. Then also we discuss something like this: if A and B belongs to script F and A is contained in B, then probability of A will be less than equal to probability of B. So for this one, let's say this is B and within this we have this small set A. If such is the case, then probability of A will be less than or equal to probability of B. And probability of B minus A, you can write this one also, will be this part. So it will be probability of B minus probability of A. And in that case, probability of A will be less than equal to 1 for all A belonging to script F. Okay, so this thing we should remember. All right, next we have some properties on sequence of elements in F. So if we have something like this, that we have a sequence of elements or sets in that sigma field where an is contained in an plus 1. So this is, let's say, a1, this is a2, this is a3, this is ... an. Okay, so an is contained in an plus 1 for all n equal to 1 to however much we can go. So then probability of limit n tends to infinity an this one will be limit of n tends to infinity probability an. So what it essentially means, so this LHS, limit of n tends to infinity an. So if this is increasing, ever increasing, let's say this is the highest point. So union of a1, a2, a3 to an will be an itself. So let's say a1 union a2 union a3 to union an will be the same as an, right? Because this one, it's increasing. So the largest one will actually be union of all the sets which are contained within that set. So then this probability of an will be limit n tends to infinity probability of an. So this sets, whatever the probability is, it will come out as this probability. Okay. Similarly, if we have a decreasing sequence of elements in F, so here we have, let's say this is a1, then this is a2, then this is a3, then let's say this is an, the smallest one within. So then limit n tends to infinity an. So as n increases, we'll just go within and within and within inside this circle. So what that essentially will mean is limit of an will be intersection of an. So if I have to do from here only, a1 intersection a2 will be a2, right? Because a2 part will be common. a1 intersection a2 intersection a3 will become a3, so on. So n equal to 1 to n intersection an will be an when we have a decreasing sequence of elements in F. Okay, is this clear? All right. So now we will jump on to the classical. So far what we were doing, this did not put any assumption on the probability except the three generic assumptions, that probability of any event should be greater than equal to 0, of omega should be 1, and disjoint events, that sigma additivity rule should hold for disjoint events. Now till our 12th standard, what we have learned is the classical definition of probability. So this is a special case. Here we define a probability space sigma omega, the sigma field script f, and the probability measure p with finite omega, where the script f is the power set, and each and every element of omega is assigned a probability which is equal. And how is it equal? Since sigma is finite, let's say there are n elements in sigma. So probability of each omega belongs to sigma will be 1 by n. This mod refers to the cardinality of this set. So by cardinality I mean, so if mod A means cardinality of A, which in simple terms means number of elements in set A. Okay. So then if A is contained in omega, then probability of A will be whichever individual elements that make up A, we take a union of those, and since these are disjoint in the sample space, thus we have summation omega belongs to A 1 by omega, this one 1 by mod of omega. So it essentially is number of cases favorable to A by number of all possible outcomes. This is what we have done so far. Alright. Then we also learned about conditional probability, that is A given B. So if we have a probability space omega script f p, if A and B belongs to script f with probability A greater than equal to 0, then probability of B under the condition that A has already happened, that is B given A, will be probability of A intersection B by probability of A. And two events are said to be independent if and only if So this means if means if and only if. So this is both a necessary and sufficient condition. Okay. So probability A intersection B will be probability A into probability B. If this holds, then we say A and B are independent, not disjoint. Okay. If A and B are disjoint, then we'll have probability of phi, which will be 0. Okay, in case of disjoint. Alright, and then we could always have pairwise independence, that is probability of AI intersection AJ equal to probability of AI into probability of AJ for all IJ, I not equal to J. If this happens for any two events, then we'll say that the events are pairwise independent. And if it happens for n events, like probability of A1 intersection A2 intersection AN equal to probability of A1 into probability of A2 into probability of AN, then we say that the n events are mutually independent. Okay. All right. So here is an example which was also discussed in class, where events are pairwise independent but not mutually independent. So what was shown, let's say this is the omega that we have 1 2 3 4 elements in the sample space. Okay, so let us define subsets A 1 2, B 1 3, C 1 4. Okay, and let us assume that probability of omega equal to, so omega belonging to the here, so probability of omega is 1/4. We are assigning equal probability to each of the elements in omega. Okay, so then probability of A intersection B is 1, that is, so for all the three pairwise also and all three together, A intersection B, we have only one element common, that is 1. Okay, probability of A, we have 1 plus, so here probability of A means probability of 1 plus probability of 2, that is 1/4 plus 1/4 equal to half. That is what is shown over here. Okay, similarly for probability of B, this will be 1/4 plus 1/4, that is half. Probability of C is also 1/4 plus 1/4, that is half. Okay, now probability of A intersection B is 1. So A and B have only 1 in common. So that is probability of 1, which is 1/4. A intersection C is also only 1 is common, so the probability is 1/4. For B intersection C also, we have only element 1 in common, so that probability is also 1/4. And taken all three taken together, that also only 1 is common between these three sets, so the probability is 1/4. So all these elements AB, AC, BC, so they are all pairwise independent. But when we do this one, probability of A intersection B intersection C, then this one is 1/4. But if we make a product of individual probabilities, then we have 1/8. So these are not matching, not equal. So that means A, B and C are not mutually independent. Is it okay? So one thing that we should keep in mind is that pairwise independence doesn't mean mutually independent. All right. Here again we had some other properties on conditional probability. So if this is a probability space and probability is a probability measured over omega condition on A, then probability A given A equal to 1. And if A and B are disjoint, then probability B given A equals 0. Why? Probability B given A means probability of B intersection A by probability of A. Now since this is disjoint, it will be probability of phi by probability of A, which will be 0. Okay. And also we have another property, probability of B intersection C given A equals to probability of B given A intersection C into probability C given A, if this A intersection C is greater than 0. So whenever we are defining, one more important thing, whenever we are defining conditional probability, so let's say probability of B given A equal to probability of B intersection A by probability of A, we should note that this event, whatever will come in denominator, that probability should always be greater than 0 for this conditional probability to be defined. Probability cannot be negative, and even if it is 0, then the conditional probability is not defined because we have some denominator by 0. So this is one small thing that we should keep in mind. So here also same, probability B intersection C given A, they are writing it as probability of A intersection C, B given A intersection C into probability of C given A, if this one is greater than 0. Okay. So this one we can also call it as a multiplication rule. So let's say if we have n events defined on the sigma field with intersection of all these events greater than 0, then by product rule we can write probability of A1 intersection A2 intersection AN as probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2, and so on. This is the product rule or multiplication rule.
Ma'am, why did they take an minus 1 in the second part?
Because if we solve this one, then only we are going to get it. So I'll tell you what happens. A1, this one, if we, let's solve from the RHS. Okay, so probability of AN given A1 intersection A2 intersection AN minus 1, this will be what? Probability of AN intersection A1 to AN minus 1 divided by probability of A1 to AN minus 1. Now imagine this one. This will be AN minus 1 given A1 intersection A2 intersection AN minus 2. Just the previous element. So if we again expand this one, what we'll get? Probability of a1 intersection an minus 1 intersection a1 intersection a2 to intersection an minus 2 by again probability of intersection of I equal to 1 to n minus 2. So can you see this one and this term will cancel out?
Yeah, the denominator and numerator.
Yeah,
is-
this denominator and numerator will cancel out.
Yeah.
Similarly, if we write the next term, this one and the next one will cancel out.
Understood.
And so on and so forth, we would ultimately land up at an intersection a1 to an minus 1. So if you just rearrange, this is intersection, right? So
Yeah.
it will be this thing, the entire thing.
Okay.
Okay, so this is the multiplication rule. The same multiplication rule was also applied here if you can see carefully. So here probability of B intersection C given A is nothing but B intersection C intersection A by probability of A. So what they are doing, they are essentially introducing another denominator, probability of C intersection A, into probability of C intersection A by probability of A. So this then becomes probability of B given A intersection C into probability of C given A. Is it clear now why this term should be greater than 0? Because we are just rewriting it in this form.
Yes, ma'am.
All right. So from here we have this multiplicative rule. Okay, so multiplicative rule states that probability of a1 intersection an will be probability of a1 to probability of a2 given a1 into probability of a3 given a1 intersection a2, so on and so forth, to probability an given a1 intersection a2 intersection an minus 1. So this is the general multiplicative rule, general case. Now what happens if a1, a2 and an are mutually independent events? So if they are mutually independent, if all are mutually independent, then probability, if we a2 given a1 is probability of a2 intersection a1 by probability of a1. Now mutually independent means pairwise also independent. Okay, all are independent. So then this one would be probability of a2 into probability of a1 by probability of a1. This one and this one will cancel. This will become probability of a2. Similarly, probability of a3 given a1 intersection a2 will be probability of a1 intersection a2 intersection a3 by probability of a1 intersection a2. Mutually independent, so probability of a1 into probability of a2 into probability of a3 by probability of a1 into probability of a2. This one cancels, so we have probability of a3. So from here we have a1, this one boils down to probability of a2, this thing boils down to probability of a3. So when all are mutually independent events, then intersection of all the events, that probability will become product of individual probabilities. Okay, this is the theorem where a2 an are mutually independent. So the thing is that pairwise independence doesn't imply mutually independent. but mutual independence implies pairwise also. Okay. Next, we also discussed the total probability rule. So let's say A1 to ... be a sequence of events in script F, that is the sigma field defined, such that ai aj equal to 5 for all I not equal to j. That is, all events are pairwise disjoint. Okay, and union of ai is adding up to omega. Then for any event b, we can break it up to summation I probability of b given ai into probability of ai. Okay, if we just expand it, what will happen? Summation over I probability of b section ai by probability of ai into probability of ai. So since these are all separate, so intersection of b with we'll get total b if we partition the intersection between the ais as well. Okay, so for any event b, we can write probability of b as probability of b given ai into probability of ai, because the entire omega subset is partitioned. So let's say this is omega, this is partitioned into some a1, a2, a3, a4 and a5. Okay, and let's say this is your this is my b set. Okay, so probability of b will be summation of these individual intersections of b with the partitions that follow, and that can be written in this manner. Can you correlate this diagram with this theorem that is being written over here? So the entire sample space, this is very important. This sample space is divided into disjoint sets a1, a2, a3, a4. So any set, so let's say this is script F. So for any set b in that script F, we can find out probability of b as their sum of intersections with these individual partitions, and that we can write in this form, provided that probability of ai is greater than 0. Okay, and also we learnt about Bayes theorem or Bayes rule, which is that for any event b in script F with probability b greater than 0, ai given b equal to probability of ai to probability of b given ai by summation of probability of aj into probability b given aj for all I. This one is I, sorry. Okay, so this will give us the Bayes theorem. Alright, and this Bayes theorem, there are two concepts, which is the priori and posterior, prior and posterior. So if A1, A2 be finite or countable partition of omega with probability of AI greater than 0, and if B is an element with PB greater than 0, then probability of AN, the sequence is called a priori distribution because it is already known, and B given this thing is the posterior distribution. Okay, so whatever is known, A to AN is known, so those are prior. And whenever we say that B, when we update these AIs based on what has happened in event B, that is called the posterior distribution. Okay, so we'll learn more about these Bayes theorem and posterior distribution in subsequent classes, but this was all that was discussed during week 1 lectures. So far anybody has any doubts? If not, then I'll just move on to the a very few problems and very basic ones. Anybody has any problem or doubt? Okay, so then we'll start with very basic problems. So suppose that I think everybody can read the question, right? Okay, so let's say there are 6 good eggs and 2 rotten eggs that have been mixed up. So to find the eggs, we test then one by one at random and without replacement. Then what is the probability that the rotten eggs are in first 2 tests? So if both rotten eggs, so the things that we should keep in mind here is without replacement. So there are in total how many eggs? 8 eggs, out of which 6 are good and 2 are bad or rotten. Okay, so in first 2 tests, so let A1 be outcome in first test and A2 be outcome in second test. Okay, so we want to find out, okay, A1 is not outcome, rotten in first test, and A2 is rotten in second test. Okay, so here we want to find out that both eggs are in first 2 tests. So A1 also rotten, since there are 2 eggs only, so A1 also rotten and A2 also rotten. Now here we are taking these as one by one and without replacement. So it's not so this thing, whatever we need, that both rotten eggs, so in first trial, how many what is the probability of getting a rotten egg? We have 2 rotten eggs in total and 8 total eggs. So out of 8, 2 could be rotten. The second event is that what is the probability? So with it, this is without replacement. So we are not putting that rotten egg in this thing. So once we already have the first rotten egg, so we are left with 7 total eggs, out of which only one rotten egg remains. So the required probability is 2 by 8 into 1 by 7, that is 1 by 28. How much do we get this as? This will be something around, so if we have to report up to 5 decimal places, it will be 0.0357 something. Okay, so this is understood. So first trial we have 2 eggs, 2 favorable rotten eggs and 8 total eggs, and the second trial we have 7 total eggs and out of which 1 is rotten. So the required probability is 2 by 8 into 1 by 7, that is 1 by 28. Is it okay? Alright, so the next one is this. A man and his wife appear in an interview for 2 vacancies in the same post. The probability of husband's selection is 1/7 and the probability of wife's selection is 1/5. So then what is the probability that only one of them is selected? So probability 1 is selected will be probability man selected and wife not plus probability man not selected and wife selected. Okay, so this one, selection of a man and the wife, they are independent events, right? So here we'll have probability man selected into probability wife not selected plus probability man not selected into probability of wife being selected. So this one, probability of man getting selected, probability of selection is 1/7. Wife selection probability is 1/5. So selection is 1/5. Then not will be selection. If A is selection, then not will be A complement, which will be 1 minus 1 by 5. So it will be 4 by 5. So here we will have 4 by 5 plus probability man not selected, that is 1 minus 1 by 7 plus wife selected, into wife selected. So we will have 4 by 35 plus this will be 6 by 35, that is 10 by 35. So it will be 2 by 7, 0.28 something, 2857. Is it clear?
Yes, ma'am. Ma'am, actually, is the next problem something related to in a box there are 8 red, 7 blue, and 6 green?
Yes.
Yeah, and after that we have in a class 30% Hindi, English, that type of problem, right? So I think that like some of us who are attending it today have already completed these problems in yesterday's session.
Okay. So the sessions are designed in such a way that I mean, so these are parallel sessions, not necessarily all individuals are going to attend the same sessions.
Okay.
So if I don't know if you've already attempted this one, then I'm afraid the following few problems there will be overlaps, because it's designed in such a way that it's expected that there'll be some people who are joining new.
Okay, got it.
All right. So yeah, if you so I can do one thing. If you plan to attend the next sessions, and I'll try to keep some other problems as well, so that it's fairly balanced for both the
Yes.
groups of people. Okay. So yeah. So this thing, maybe you can help me out. So how many of you have already attended yesterday's session? 1, 2. Anybody else? Okay. Fine. Okay. Thank you for this input. I'll try to keep this in mind from the next class. Alright? Okay. So, as I was saying, in a box there are 8 red, 7 blue, and 6 green balls. So one ball is picked up randomly, and what is the probability that it is neither red nor green? So if it is neither red nor green, then it should be blue. So the favorable event is 7 by total 15 plus 8 plus 7 plus 6. That is 7 by 21, 1/3, 0.333. Okay. Others, can you follow? All right. So then the next problem is, in a class 30% of students are offered English, 20% are offered Hindi, and 10% offered both. So let A be an event that is representing percentage offered English, B be the percentage, so probability A is English, B is Hindi. So probability of A is 0.3, probability of B is 0.2, and 10% offered both means probability of A intersection B will be 0.1. Then what is the probability that he has offered Hindi or English? So we have to find out probability of A union B. So this will be probability of A plus probability of B minus probability of A intersection B. So here we would have 0.3 plus 0.2 minus 0.1, that is 0.4. So there is a 40% chance that he has been offered Hindi or English. All right. The next one. So if we consider an event of tossing a coin, and the outcome of each event is observed until 3 consecutive heads are observed or 5 consecutive outcomes are observed, then find the sample space of this experiment. So how can we proceed? Any of you who have attended yesterday's session, can you answer this one?
Yes, ma'am. So basically, like there are four options, and then we need to eliminate some of the choices. Like, for example, in the first one, we have three heads. So this is valid. Next, we have like basically it has to be three consecutive heads, or it has to be five outcomes. If it's not three consecutive heads, we'll immediately eliminate that option and go for the next one.
Okay. So then how should you proceed?
So, like for the first option, we have HHH, that's correct. Then triple HT, that's also correct. Uh, T triple H, that is also correct. But the next one is wrong because we don't have three consecutive heads, nor do we have five outcomes. So it's wrong.
Okay. So this is
And
eliminated then.
yes, then we have three consecutive heads. That yeah, we can go for the next option. Yeah, then after that, we have three consecutive heads. Here we have five outcomes at the same time. We have three consecutive heads, so it's valid. And then again, we have three consecutive heads, that's correct.
And 5.
And five outcomes at the same, yes.
Okay.
And then this one is also valid since we have five outcomes.
Okay.
And similarly, this also has five outcomes. That also has five outcomes. And the next one also, three, four, yeah, the next one also. And after that, means option B is the correct one. So,
Option B is the correct one. So what is the difference between this one and option 3? Why is option 3 not correct?
because in option three, 1 minute. There might be some outcome where we might have
So here we have 3 consecutive heads.
yes.
Here also 3, here also 3, here also 3. So the point of difference is this one.
Yeah, that doesn't have a three consecutive.
That doesn't have 3 consecutive heads, but it does have 5 outcomes. Then why is this not?
I'm not sure why didn't we consider this option.
Yeah, even I am not sure. So D is also incorrect because here we have 4 outcomes and neither is consecutive.
If I'm not wrong, I think she made an edit yesterday. She cancelled one of the head. It was supposed to be double H, double T.
Okay, all right.
I will just one minute.
All right, all right.
Yeah.
So in this case, this both B and C are correct options. Because here all of these are 5 tosses, and here even though we do not have 3 consecutive heads, we do have 5 outcomes observed. So this will also hold. All right. Okay. So let's consider this one. So let omega, F and P be a probability space. Omega has 5 elements where these are the probabilities associated with each of the elements. So if we add all up, 2, 2, 1, 5, 3, 2, 5. So P of omega is coming out to be 1. Okay. So find the sigma field for the same. So here also we will follow that elimination approach. Okay. So let's start with this one. This is the power set. So power set will also always be the sigma field. Okay. And F0 omega is also the trivial sigma field. Is option C a sigma field? I don't think option C is a sigma field. Can you tell me why?
Ma'am, this question was not covered in yesterday's session, but I'll give it a try. I think we don't have a complement for A.
Exactly. So if A belongs to script F, A complement is what? A, C, D, E. This doesn't belong to script F. Similarly, for B also, A, C, D, E doesn't belong to script F. So then this is not a sigma field. Okay? And D is also not a sigma field. Can you tell me why? Because this complement, that is E, is not present.
Basically, D complement is not there in this.
D complement is not there. ABCD complement is not there. Then if we take, for this one also, if we take union of all these, then we would have, oh, that is there, sorry. If we take union, then that is there. A, B, C, D, E. But if we take A, B, C, C, these three unions, if we take, then set ABC is also not present here. So these two are definitely not sigma fields. Okay? But A and B are. Alright. Then this one. Was this given in yesterday's session?
No, ma'am. Like there were no questions related to sigma fields or so. It's
Oh.
it was only about probability.
Okay. So then give this a try. Which of the following are sigma fields? Give with when an experiment with omega we have A, B and C. So is this a sigma field?
No, because we don't have a.
Because A complement will be BC, which is not present in script F. Okay, and also omega should be present, no? So omega is present, sorry. Omega and phi are present, sorry, my bad. This is not a sigma field. What about this one?
We don't have a complement for AB, nor we have a complement for BC at the same time.
Exactly. So this is also not a sigma field. What about this one?
That is a sigma field since we have both the complements.
Yes, since we have omega and sigma. This is a trivial one. So this is correct. All right. This one was covered?
Yes, ma'am. This was also.
Okay. So can you say how you solved this?
So, like, it's given that P of A union B is greater than or equal to 3 by 4. So, we can use the definition that is A union B is equals to P of A plus P of P minus P of A intersection B. That we can express it as greater than 3 by 4, greater than or equal to 3 by 4.
So this is the expression. Now you tell what you were telling.
This expression, like the RHS side, is greater than or equal to 3 by 4, right?
This is greater than equal to 3 by 4. Correct.
So like with the help of inequality rules, we can shift that A intersection B on the other side, like 3 by 4 plus P of A intersection B uh, is, yeah. And we can consider the lower limit since it's given P of A intersection B is less than equal to 1 by it, so that we can write 1 by it, and then
This one will hold.
it will be 7 by 8.
Okay, P of A intersection B is greater than equal to 1 by 8.
Yeah,
So can I write this thing as P of this is greater than half?
yes, we can write.
Okay, and okay,
It's greater than 7 by 8, so we have proved the statement 1.
it's
3 by
greater
4
than
plus
equal to half and it's greater than equal to 7 by 8. Have we really proved?
a 3 by 4 plus 1 by 8, that will give us 7 by 8, right? So
Yes. So
so P
here
of
I
8,
made a mistake. Yeah,
yeah,
8. Yeah, this is 7 by 8.
yeah.
So statement 1 is proved. All right. What about statement 2?
We can do it similarly by taking uh, the upper limit, that is 3 by 8.
So this is true. So can we write it like this? A plus probability of B minus probability of A union B.
Yes.
So this is greater than equal to 3 by 4 minus 3 by 8. Or no?
Mm,
So probability of A intersection B, sorry, this is greater than equal to 1 by 8, but this is less than equal to 3 by 8, right? So this entire thing should be less than equal to 3 by 8.
yes.
So then probability of A plus probability of B should be less than equal to 3 by 8 plus probability of A union B. Then how can I proceed?
We are given that probability of A union B is uh, greater than equal to 3 by 4. So
But here we have less than equal to, no?
yeah,
So we have to prove probability of A plus probability of B is less than equal to 11 by 8. And here we have probability of A intersection B is less than equal to 3 by 8. So this one will be 3 by 8 plus probability of A union B. So probability of A union B, the minimum value is 3 by 4. This is greater than 3 by 4. So if we put this as the minimum value only, 3 by 4, then what do we get here? 8.
Yeah, 9 by 8.
We get it to be 9 by 8, but not 11 by 8.
Yes.
So how can we get this to be 11 by 8? It's very simple. Any probability will not exceed 1. Right?
Oh, 11 by 8 is greater than 1, so it doesn't make sense.
So no probability will exceed 1. So then this will be less than equal to 3 by 8 plus 1. Because this will always, maximum it can go up to 1. So then it will be 11 by 8. Is it clear? Is it clear to everybody else? No probability, since if you remember, probability will map from that set to 0 to 1. So no probability will ever exceed 1. So if we take this thing, here we already have that probability of A. So we started from here, okay? Then we just interchange sides. So first we took this to this side, probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. So we already know that probability of, so taking this thing, we have that this entire thing, probability of A intersection B, it's given to be less than or equal to 3 by 8. So the entire thing should be less than equal to 3 by 8. So now probability A plus probability B, taking this one to this right side, we'll have 3 by 8 plus probability of A union B. Now this one can never exceed 1. So it will always be less than 1 or equal to 1. So we'll have 3 by 8 plus 1, that is 11 by 8. So both the statements hold true. This thing we have gotten. Now we have to, so C and D options are not correct. So now they are saying that both statements are true and statement 2 is the correct explanation of statement 1. Or both the statements are true and statement 2 is not the correct explanation of statement 1. So here this thing is holding irrespective of this 7 by 8. Nowhere in this equation have we used 7 by 8. So given these information, this will always hold. So neither is the correct explanation for one another. Okay, so the most appropriate option is B. Both the statements are true and statement 2 is not the correct explanation of statement 1. Is it okay? Any doubt? Alright. So I'll move on to the next one. So this one I think has already been covered, is it?
Yes, ma'am.
Oh, okay. So really sorry, I'll try to keep these things in mind from the next class and bring in some new problems. So the thing is, the probability that this person, Sita, Geeta and Ramesh, each passing a test is 60%, 40% and 20%. So what is the probability that Sita and Geeta will pass and Ramesh will not? So Sita, Geeta and Ramesh, these are there are two options, either pass or fail. Okay, and their passing and failing are independent of each other. Okay, this is the assumption. So then probability that Sita and Sita passes and Geeta passes and Ramesh fails. It will be probability of Sita passes into probability of Geeta passes into probability of Ramesh fails. So then this will be, passing probability of Sita is 0.6, 0.6, of Geeta is 0.4, and Ramesh is 1 minus 0.2. So we'll have it something like, what will this be? 0.6 into 0.4
192.
into 0.2, 0.192. So the answer is, what is the probability? The answer is 19.2%. That is option D. Okay. So this one was also discussed.
Yes, ma'am.
All right. So in a race, the odds in favor of cars P, Q, R, S were 1/3, 1/4, 1/5, and 1/6. So what is the probability that one of them wins the race? How will you solve this? How did you solve this question? So probability, yeah, say.
Like, so this is just the odds in favor, so the probability would be like 1/4 for P, and then for Q it becomes 1/5, for R becomes 1/6, and then for S it becomes 1/7. That's the probability, but here it's given in odds in favor, so
Exactly.
that's the catch.
Okay. So odds of P winning is 1 in 3. Odds in favors of car PQRS are 1:2. So how do you convert odds to probability?
So like we have it's like 1 and 3, so we add and then use that as a denominator. Like if it's 1:3, then
Okay. So whatever I've written here, it's actually incorrect.
yes.
These are not the probabilities. These are odds. Okay. So odd is 1:3. So it means win 1, lose 3. So probability will be 1 by 1 plus 3. That is 1 by 1 plus 4. 1 by 4. Similarly for this one, odds are 1:4. So if we conduct 5 matches, so win will be 1, loss will be 4. So probability of winning will be 1 by 5. Similarly for R, probability of winning will be 1 by 6, and probability of winning for S will be 1 by 7. So then what is the probability one of them wins the race? So this will be P wins plus Q wins plus R wins plus S wins. So if P has to win, then it should be 1/4 into 4/5 into 5/6 into 6/7. So this is 1/7 plus Q wins, that is 3/4 into 1/5 into 5/6 into 6/7. So this will be plus R wins will be 3/4 into 4/5 into 1/6 into 6/7, and plus S wins will be 3/4 into 4/5 into 5/6 into 1/7. So if you calculate, how much do you get this to be? So we'll have 1/7 plus 3/28 plus how much did I write this to be? 4, 4/5, 4, 4 cancels, 6 cancels. So this will be 3/35 plus here again 3/42. How much do you get this to be? Is it something around 0.407?
Yes.
Okay. So did you get this, Sridip, yesterday as well?
Yes, ma'am. Like
Okay.
in this one.
Okay. Please don't call me ma'am, like call me Shreya. It's okay. Yeah. So I think I am nearing the end of the session for today, and I do have a few more problems, but I think those have also been discussed in yesterday's session. But if you want, I can quickly go through them. So this was discussed. These are very basic problems.
Yes, yes.
Okay, so these were also discussed.
No, this one was not discussed. So,
Okay. This one?
no, none of these. I don't think any other like
Okay.
different.
Okay. Let us discuss this then. And if A and B are independent events, then which of the following is not correct? So A and B are independent. A and B complement, are they independent?
No, wait. I'm not sure on this one.
So if A and B are independent, A and B complements are also, these three will also hold, but they are not mutually exclusive. This might hold, but this will never hold, because that's what I was saying. Mutually exclusive means this thing.
Yes.
So probability of 5 will always be 0 and in that case. So which is not correct? If two events are independent, they may not be mutually exclusive. They will not be mutually exclusive. This is not correct, okay? So this is something you should bear in mind. And these things I think you'll be covering later. Okay. So I think in subsequent classes we are going to cover more of these descriptive statistics related things. Have you had any idea of expectation and variance?
Yes, ma'am. Mathematical expectation and
Okay,
the
okay. Okay, so fine, we'll just discuss these concepts and then probably move on to these questions. Meanwhile, in any feedback on today's class, what you want to know, because I really didn't know with what expectation you came. So if you can give me some feedbacks for the next session, that will be extremely helpful for me and as well as for the attendees of this session. Anybody? Okay. If not anything, then thank you so much for attending this session. Hopefully, I'll keep the inputs that you all gave me in mind for the next one, and I'll try to bring some problems which will not be discussed in Friday's sessions, and some new session for this Saturday's session. All right. Okay. Thank you so much for joining. And if you still have questions related to this session or anything else, please use the discussion forum. The TAs are there to help you out, and they'll probably answer the questions and clear all your doubts. Okay. Thank you for joining. Have a nice day. See you
Thank you.
next week. Thank you. Bye bye.